Hello students, today we're going to talk about infinite series. An expression in the form a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and so on is called an infinite series. This is very similar to a sequence, except instead of a list of numbers infinitely long, it is a sum of numbers infinitely long. We've got a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, etc., etc. And the three dots here mean we continue to add indefinitely. Now you might be wondering, how can we keep adding forever? And this is somewhat at the intersection of math and philosophy. If we have to keep adding forever, for example, how can we even know we've arrived at our answer? This might seem a little bit intimidating or abstract, but the fact is that in certain circumstances, if we keep adding smaller and smaller quantities, we're going to end up with a finite number, and I want you to consider the following situation. Suppose that you have a birthday cake and you want to eat it in a very, very particular way. On the very first day, on your birthday, you decide you're going to eat half the cake. Then on the next day, you eat half of what remains, which in this case is a fourth of the total cake. Then the next day you eat half of what remains, which is 1/8 of the original cake, etc., etc. And you keep eating half of what remains every day. Now this process can continue forever because there's always some amount of cake remaining. Whenever you eat half of what's remaining, that means you've also left half remaining, and you're never eating all of the cake that's remaining, so you should be able to continue doing this forever and ever. And we can express the amount of cake that we've eaten as a series. On the first day, you've eaten 1/2 of the cake. Then on the next day, you've eaten half of the remaining bits. That's 1/4 of the total cake. Then on the next day, you've eaten 1/8. Then you've eaten 1/16. Then you've eaten 1/32. And this continues on indefinitely. And so this is an example of an infinite series. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, etc., etc. Now there's two things that we can definitely say about this. The first is that no matter how many terms we add up in this infinite series, we're never going to get an answer that's larger than 1. And the reason is we only started off with one whole cake. And so as we're eating half and half and half of what remains, we don't have more than one cake to eat. So the total amount of cake that we've eaten cannot be more than 1. However, it's also a fact that as we eat more and more cake, we're getting closer and closer to having eaten the whole cake, because the amount remaining is getting smaller and smaller and smaller. So this suggests that this total sum, this infinite series, is equal to 1, because it can't be larger than 1 because we can't eat more than the one cake that we have. And also, it's getting bigger and bigger and bigger, so it's approaching 1. You might even think it's approaching 1 asymptotically, if you remember some of the graphs that we've seen this semester. And so, in general, if we were to keep eating and eating and eating forever, we would get closer and closer and closer to eating the whole cake, and in the end of time, we would effectively be eating that one cake. Now, there's a lot of philosophy that's going on here, and I don't want us to worry about the philosophy. I want us to worry about the mathematics. And so what we're going to do is we're going to look at this infinite series by examining the partial sums and seeing what's happening as the days move on. So the first partial sum, remember, is just the first term. In this case, it's 1/2. The second partial sum is 1/2 plus 1/4, which is 3/4. We've actually already done these calculations in a previous lesson, so I'm not going to show all of the fraction arithmetic. The third partial sum is 1/2 plus 1/4 plus 1/8, which is 7/8. The fourth partial sum is 1/2 plus 1/4 plus 1/8 plus 1/16, which is 15/16. And if we look at what's happening to these partial sums, the denominator of the nth partial sum is 2 to the nth power, and the numerator is 2 to the nth minus 1. So the nth partial sum is 2 to the nth minus 1 all over 2 to the nth. Now we can rewrite this as two separate fractions. 2 to the nth over 2 to the nth minus 1 over 2 to the nth. And the first fraction just reduces to 1. So we've got 1 minus 1 over 2 to the nth power. This is an expression that represents the nth partial sum. But because we're looking at an infinite series, we want to know what happens to the partial sums as n gets bigger and bigger, as the days go on and on. And as n gets bigger and bigger, 2 to the n gets exponentially large. We've seen exponential functions. We know how this works. And when we have a fraction where the numerator stays constant and the denominator is growing exponentially, that fraction is actually getting smaller and smaller and smaller. And so if we look at this expression, it's 1 minus a fraction that's getting smaller and smaller and smaller. What's happening to this is that it is approaching 1. It's getting closer and closer to 1 as n is approaching infinity. So this is very similar language that we've used when we were looking at asymptotic functions and end behavior of rational functions and similar things. So in this case, because the partial sums are getting closer and closer to 1 as they're approaching 1, as n approaches infinity, we say that 1 is the sum of this infinite series. We conclude 1 is the sum of this infinite series. And in general, if we look at our partial sums and they approach some finite number s as n approaches infinity, we say that s, that number, is the sum of the infinite series. This is actually how we define the sum of an infinite series. If the partial sums are approaching a finite number, then we say that that number is the sum of the series. We're going to, in the next video, focus on infinite geometric series because those are the easiest ones to deal with. But I do want to quickly mention that in Calc 2, there is an entire unit that's devoted to infinite series and determining whether or not they have a sum, or they go to infinity, they keep getting bigger and bigger, or something else happens. And it's a really rich branch of calculus. And we're looking at this now so we can get a taste, and so that when you get to Calc 2, it's just a little bit easier to digest. So do your best to digest this philosophical, confusing complicatedness, and ask questions when you have them, and you will be much better prepared when you get to Calc 2.